Welcome to SAR 3. Our next talk is called Hacking the Universe When Strings Are Super and Not Made of Characters. It's going to be held by Robert Helling. It's a talk about physics and the ideas about the nature of space and time, and the answer to the ultimate question of life, the universe, and everything, I guess. And I'm very excited to hear about that. Please give a round of applause to Robert.
Hello. Before I start, I wanted to thank a number of people, mainly you, for coming. Since this is not on the main track of the conference and you're still awake on day 4 to hear something which is slightly off topic, but I hope to convince you that it's not so off topic at all. So, usually I speak in front of other audiences, and I don't know most of you, and probably you don't know me. So, before I do this, first I'm going to introduce myself in 1 or 2 slides, and I decided to talk about 3 particular subject areas, and this gives you the 3 main parts of my presentation. So the first, I talk about cosmology, which is that part of physics which deals with the universe as a whole. Then the second part is about particle physics, and I guess all of you have heard about LHC, that finally came up a few weeks ago and is now, well, after the winter break, about to take first data. And then the last section is about string theory, which is a proposed theory you might also have heard about, that is there to unify gravity and quantum physics. And when I introduce these 3 topics here, I should say that my own area of expertise is this. I'm a string theorist, but I've also worked on cosmology. I have not worked on experimental particle physics, so this part is, I read this. I'm not actively working on this. And I finish, maybe if I have time, with some speculation on whether it's possible to have open source physics. So, who am I? My name is Robert Helling. If I don't use my real name, I use my other name. I do research on string theory and a number of other things. I work at Ludwig-Maximilians University in Munich, and I've been at some other places, and in the net you can find me here. To introduce myself, this was my first computer. This was the first computer that worked. This was my first modem, and it didn't work because this was our telephone. And you see, round, not round. But I was introduced to this, and from that time I was taken. So, why am I here? Why am I speaking about hacking the universe? And that is because I'm deeply convinced what we do when we do physics is also hacking. So what is hacking? Let's go to the jargon file. Who's a hacker? A hacker is a person who enjoys exploring the details of programmable systems and how to stretch their capabilities as opposed to most users. Well, if you forget about programmable systems, this is pretty much what we're doing. We're trying to explore the details and stretch the capabilities of what the world offers to us. And in particular, it also cites RFC 1392, where it says, a person who delights in having an intimate understanding of the internal workings of a system. So, and that's what we do with the universe, and its parts up to the smallest scales. And the other slogan I copied from Make magazine, if you can't open it, you don't own it, and of course we want to own our world. Okay, let's start with the first subject, which is cosmology, which is about models of the world. And I always start with saying until the 1960s, this was mainly speculation and guesswork and broad extrapolation of something you know what you do in the lab to very large scale. So it brings you to pictures of the world that are only quantitatively better than this one with the Earth on number of elephants on a turtle. Yeah. So, but now I'm going to move forward to a little bit later. I mean, this is a very recent picture, but in the 60s, people discovered, had similar things, not with this fidelity. This is a picture of the Hubble Space Telescope, where they pointed the Hubble Space Telescope at an empty area of the sky. So there's no star in this picture, at least when you look at it with your bare eye. So they pointed the Hubble Space Telescope into a dark area of the sky and looked at it for 48 solid hours. And this is what they found. And every little dot here is a galaxy, right? And this is pretty much as far as we can see in the sky. And we have good understanding what's going on here, all these little dots. And I would particularly point to the dimmer, redder ones. These are the furthest away structures that we can see in the nearly optical spectrum. So this is what we see of the universe. This is the universe. And when we look at these pictures, people discovered, namely Hubble, that you just not look at the pictures, but you do measurements. And two things you can measure with some tricks I'm not going to explain is first a star's or a galaxy's distance, and another thing you can actually more easily measure than this is the star's velocity relative to us. This you see from the Doppler shift and looking at the star spectrum. And what people found is that roughly the star's distance is proportional to its velocity. So the further something is away, the faster it moves away from us. And to explain this, there are two possibilities. First is we're in the center. Not very likely. Possibility two is the universe as a whole is expanding. But still looking at these pictures, this is not really, doesn't say everything. For example, it could be that the universe is constantly expanding and has been doing this forever. And matter is created out of nothing when the space stretches. That was a serious theory in the 1960s. And its contender was the Big Bang theory, which says, okay, this hasn't been going on forever. There was a point in time where everything was together, and then it exploded in a huge bang, and stuff has flown apart. But how can you tell? From these pictures. Well, let's go to New Jersey, 1965. People were experimenting with the first telecommunication satellites. This is a picture of an early telecommunication satellite. You see people here. So this is just a big balloon, which is with metal coating. So what they did is they just flew this in the air, very high, and then pointed a radio transmitter towards this thing, and on some other continent, they tried to receive the reflected stuff. So it's completely passive. There's no electronics here. That was telecom satellites very early. And this is the antenna that they used to pick up the signal. There's a huge microwave antenna. And this was constructed by people at Bell Labs. That's the Bell Labs of Kernighan and Ritchie. And they had a problem. They couldn't get rid of some noise in the antenna. Whenever they pointed it to the sky like this, there was some residual noise, and this noise is measured in temperature. They measured a noise temperature of 3.3 Kelvin. And they were tuning everything. They were removing the pigeon leftovers from the antenna with still noise. They couldn't get rid of it. And then they talked to people at Princeton University, and those people, the physicist in Princeton told them, actually what you see is not noise. You see the Big Bang. This is the afterglow of the Big Bang. It's the heat radiation that's left over from the Big Bang, which has cooled down to this temperature. And people had speculated about this before when they thought about Big Bang theory. And these people, Wilson and Penzias, discovered this afterglow. They got a Nobel Prize for this not too long ago. And then people actually precisely measured this, and they discovered it's the most perfect black-body spectrum that you can find anywhere. It's absolute thermal radiations coming from all directions in the same way. Only the number is actually